Good morning, everybody. Welcome to Samvaad-Talk. So today we have the second talk in the theme on cyber security. And today's talk is by Gayathri Garimella. I would like to now invite Professor Ashish Choudhury to chair the session. Thank you.
Thank you, Jaya. So, welcome everyone for today's talk. Let me quickly give you a brief biography of today's speaker. So, Gayathri Garimella is a third year PhD student at Oregon State University, advised by Dr. Mike Rusule. Her research focus in recent years has been studying private set intersection, variants, and extensions. Previously, she was a student of the Integrated Master's Program at IIIT-Bangalore. During her time here, she was introduced and mentored by myself in the field of cryptography. She also spent many summers of her undergraduate studies at Cryptography and Information Security Lab at Indian Institute of Science, hosted by Professor Arpita Patra, working on consensus and broadcast protocols in the topics of distributed computing. So over to you, right?
Thank you so much for that introduction. It feels great to be back at IIIT Bangalore, even if it's just virtually this time. So let's get started. The theme for today's talk is private set intersection, and then moving towards the ultimate goal, which is private analytics. And I've spent the last 3 years studying and working on this problem. And hopefully through this talk, I'll be able to convey some interesting ideas and themes from studying PSI. So a quick note on what to expect in today's talk. I'll be talking about what private set intersection is and mentioning some of its applications. Then we'll consider various approaches towards designing a PSI protocol and work our way towards building a PSI protocol using a primitive called vector OLE. Then we'll switch gears a little bit and we'll ask the question, what can we do beyond intersection and consider other set operations? So I'll partially describe constructions to realize something called intersection sum of associated values and also to get the set union. And finally, some concluding remarks about the various problems in PSI research and the various dimensions and angles through which you can approach it. So without much ado, let's get started. What is private set intersection? So this is Alice, and she has a set X, and she cares about the privacy of this set. She doesn't want to reveal this set to anyone else. And this is Bob. He has his set Y, and he doesn't want to reveal the contents of his set to anyone else either. And for some reason, Alice and Bob together want to know the items that they have in common, otherwise known as the intersection of the set. So in this case, we want Bob to learn the intersection of X and Y, which are the letters L, A, and T. And we want to ensure that Bob learns only the common items and nothing else. That is, he's not able to learn, say, the letters V or I from Alice's set because they don't belong to the intersection. And similarly, from Alice's perspective, she should be completely oblivious of the items in Bob's set. Okay, so here's another quick example. And this is just to illustrate that the set items can really be anything. For instance, it could be the set of clients that Alice is working with and the set of clients Bob is working with. And here it makes sense that Alice doesn't want to reveal one of her clients, say Target, which is a client that is unique to her and doesn't belong to both Alice and Bob. So this is a neat and clean and rather cute abstraction of what PSI is. You have Alice, you have Bob, and it looks really nice and simple. But let's see what PSI actually looks like in the wild. What are some real world use cases of PSI? Where would something like this be applicable? So the first example that I'll talk about is known as private contact discovery. So this is an article that talks about a messaging application called Signal, and they've been dealing with this problem called private contact discovery. So what they would like is that whenever someone installs the Signal application, they want that person to learn which of their contacts also uses this application so that they can message them so that they can message them directly on the Signal application. And they want to do this in an efficient and scalable manner without having to reveal their private contacts to the Signal service. Here it would be the Signal server. So let's see how PSI would help here. So look at Alice, and she has her phone and has her contacts there. And she just installed her favorite messaging application, say Telegram. Here, the role of Bob is played by the Telegram server, which has the list of all the users who are using the Telegram service. So now Alice and the server could run a PSI protocol so that Alice ends up learning the items common to her contacts and the Telegram users. That is, whichever of her contacts use Telegram, she only learns that much. And more importantly, from Telegram's perspective, Telegram absolutely learns nothing about Alice's contacts, which is what we're looking for. So this is one place where PSI would be really useful. Let's look at another example. This is called the password checker application. So maybe you're a person who has a ton of passwords now and you're using Google's password manager and you're storing your passwords there. So Google had this nice feature, which first started as a Chrome extension feature and now is a part of its password manager. And basically, whenever you store your passwords there, it's going to highlight to you which of your passwords are insecure. And by insecure, I mean that which of your passwords have appeared in previous data breaches or in password hacks and stuff like that. So it'll highlight to you and tell you that, hey, this password looks insecure. And then you as a user would be like, okay, I'm going to change this password. So this is a really nice feature to have and something that we want. But maybe you as a user are not willing to share all your passwords directly with Google, especially when you don't know what they might do with it. So this is another classic setting where we can apply PSI. Alice has a set of passwords, and this is Google's database of all the passwords that appeared in breaches. And they run a PSI protocol, and Alice learns which of her passwords are insecure and changes them. And again, Google learns nothing about Alice's password sets. So these are just some really popular applications, but there are many, many use cases for a problem like PSI. So this is what has been making it so interesting and why people are taking a lot of interest in this problem. So before we start building our PSI protocol, I'd like to make some comments about adversarial behavior. So if you're hearing about such a problem or privacy concerns for the first time, you might wonder or think of this as a possible solution. What if Alice and Bob have another friend, Charlie, and they trust Charlie? So a simple solution for PSI would be that Alice and Bob just send their sets to Charlie. Charlie looks at them, realizes what the intersection is, and he can just reveal the intersection to Bob. Okay, so this solution works. There's nothing wrong with it, except that you have to find a trusted third party. And finding such a trusted third party in the real world is very, very hard. Like, for instance, you might initially trust Charlie, but over a period of time, Bob may be able to influence him. And then Charlie might leak some information about Alice's set to Bob. And that might be devastating depending on the application from Alice's point of view. And this can happen in the other direction as well. So the key point is that finding a trusted third party is really hard and you can't get any guarantees. So the idea is to use cryptographic techniques so that Alice and Bob can just compute amongst themselves. So they run a protocol where they just send messages to each other without relying on some external trust. And at the end of this protocol, Bob learns what he's supposed to, and it doesn't learn anything beyond that. But there exists the problem that now we have only Alice and Bob, but Alice and Bob can cheat, or one of them can cheat. And the possibility still exists. And in this, for the purposes of this talk, I'm just going to be assuming something known as passive adversarial behavior. So here, Alice and Bob will follow the steps of the protocol to the T. They're going to do as they're told, and there's going to be no unexpected behavior from Alice or Bob. So the only thing that we have to do as a designer of the protocol is to ensure that they only learn what they're expected to, and say Alice learns nothing about Bob's set and Bob learns nothing beyond the intersection. Certainly, there are stronger types of adversarial behavior where Alice can deviate from the protocol arbitrarily, or Bob can do the same. And there exist protocols, but that'll be out of scope for this talk. So I'm just going to assume that Alice and Bob completely follow the steps of the protocol. So the first question you might have, or you might wonder, why can't we use something known as generic MPC or generic secure computation? So by secure computation, what secure computation allows us to do is, if Alice has some private input X and Bob has a private input Y, then secure computation allows them to compute any function F over X and Y. So there exists, this is a field where there have been a lot of protocols that have been developed over the years. And you might wonder, why can't we just pick an off-the-shelf protocol for secure computation and apply it here? So if you want to apply a generic solution like this, you would have to encode the function of computing the intersection as a circuit. And obliviously, Alice and Bob would have to evaluate this large circuit of computing the intersection of two sets. So you might be able to see that in order to compute the intersection, you would need to make at least order n square comparisons, where Alice has n items and Bob also has n items. That is, each of Alice's items would at least have to be compared with all of Bob's set. So that would give us n square comparisons. So the circuit that we build would have at least order n square size. And a secure computation protocol would then require at least order n square communication. At the other end of the spectrum, you can think of another protocol where we don't care about privacy at all. If we didn't care about privacy and Alice and Bob just have to compute the intersection, then what Alice could do is simply send her plain set in the clear to Bob. Notice that she only sends n items to Bob and he learns the output, which is the intersection. So the communication here is order n. So these are two ends of the spectrum. So the answer to the question, can we just use generic MPCs? Certainly, of course we can. But the idea is that we want to do better than that. And we want to have better asymptotic communication than order n square. So we ideally would like to have a communication as close to order n as possible. Okay, and order n is what we get if there's no privacy at all. So that's the goal. So let's start with a warm-up PSI protocol. And this is the setting that we have. Alice has a set, Bob has a set, and both care about the privacy of the set. So you might be inclined to design a protocol using, say, a cryptographic hash function. So I'm not going to be rigorous with this. I'll just loosely explain what a cryptographic hash function is. One, it's a deterministic function, and it allows you to map arbitrary strings of any size to strings of, say, a certain length m. And one property of a cryptographic hash function is that it's really difficult to find two different values that hash to the same value. So for our purposes, you can just imagine that if you have a value xi and you're going to hash it, then it's almost like a unique mapping when you apply a hash. Another thing is, it's really easy to compute hash values. So if I give you a hash value, it's very easy and quick for you to compute the hash. But to invert a hash, it's really, really difficult. It almost requires like a brute force search over the entire domain, which is very large. So given a hash of a certain value, you can't figure out the underlying value that it's a hash of. So given these properties and understanding of a hash function, you might be inclined to design a protocol like this. Alice can just compute the hash of all her values and send it in no particular order to Bob. Okay, and from Bob's side, he can just compute a hash of all of his values. And if he ever sees any value, if he sees that any of his values, hash values, map with some of the hash values that Alice has sent, for instance, if say a hash of xi matches with hash of yj, then he can immediately conclude that yj belongs to the intersection. So this is what the protocol would look like. And you might almost believe that it works, but there is a certain problem. And the issue is that the hash function is known publicly and known ahead of time. So Bob could launch a dictionary attack. What this means is that Bob, for instance, if Alice and Bob are just computing intersection of items and Bob knows that they're computing, say, the intersection of phone numbers, then he knows that the domain is restricted to only numeric digits. And he also knows that maybe it'll be like sets of 10 digits or something like that. So he may be willing to just compute, say, 10 million hash values and create a table where he knows the value and its associated hash value. And as I mentioned earlier, it's important to note that it's really easy to compute a hash value. So it's not too difficult to compute, say, 10 million hash values. So now the issue is that whenever Alice sends her set of n values, no matter what messages she sends, Alice would have invested that computational effort already, and he can recognize all of Alice's values. So basically, Alice ends up with having no privacy at all. So as you can see, this looks, you might be inclined to believe that this works, but it will require a little more nuance to design a secure PSI protocol. So let's do just that. So I'll be designing a protocol and explaining how we can get PSI using a primitive called vector OLE. Here, OLE stands for Oblivious Linear Evaluation. And this is a simplified version of the construction of a PSI protocol from my recent paper, Oblivious Key Value Stores and Amplification for PSI. So here we're going to assume that vector OLE is a black box. So I'm going to assume that Alice and Bob can just send values to the vector OLE, and it spits out a value back to Alice. So here Bob will, so this is a description of a vector OLE. Bob will send in two vectors of his choice. So he sends in vector u, which is a vector of field elements, and he's of size n, and he sends another vector v, which is a vector of size n of field elements. And from Alice's side, she gets to pick one field element of her choice. So she picks one scalar value and not a vector. And what Alice learns as the output is a vector w, which is delta times u plus v. And just to make it really explicit, I have some examples. So if Alice's scalar is, say, 5, if the value of it is 5, then she learns a vector w, which is 5 times the vector u plus v. And if you just plug in some values, say u is this vector and v is this vector, and Alice picks a scalar, say 1, then she ends up learning just the sum of u plus v. So this, hopefully it's clear what a vector OLE is. And in recent years, there's been a line of work that gives us very efficient constructions for vector OLE. Here, I'm going to treat it as a black box, but actually it's an interactive protocol between Alice and Bob. And we're going to assume that it is possible to do this. So very quickly, for PSI, Alice has her set, Bob has his set, and you've assumed a vector OLE. So the next step is from Bob's side. What he does is, he has his input set and he encodes his input into a polynomial u. So he computes a polynomial u such that the roots of this polynomial are all the items in his set. So every time this polynomial is evaluated at a value y, it evaluates to 0 if that value y lies within Bob's set, and it evaluates to some non-zero value if it lies outside the set. So the picture on the right is just a pictorial representation of this. All of Bob's items are roots of this polynomial. Okay, and he also picks another random polynomial v, and you can represent a polynomial in terms of its coefficients. So the coefficients of the polynomial will be what the vector v and the vector u encode. Okay, and random has a very specific meaning in cryptography, but for our purposes, just assume that Bob picks some vector v of his choice. And from Alice's side, she just picks the delta of her choice, which is a value from the field, and they run vector OLE. Next, Alice looks at the output from the vector OLE, which is a vector, and she interprets it as a polynomial w. Then she evaluates this polynomial on each of her inputs, so wx1, wx2, up till wxn, and sends it in no particular order. So she just permutes it and sends it in some order to Bob. Finally, I claim that Bob can compute the intersection as follows. So he looks at his vector v, interprets it as a polynomial capital V, and he evaluates this polynomial on all of his inputs. So for instance, he computes, say, v of y1, and then he checks if he sees v of y1 in the set that Alice sent him. If he sees this value in Alice's set, then he can conclude with certainty that y1 belongs to the intersection. If he doesn't see this value, then he can be certain that y1 does not belong to the intersection. So hopefully the steps of the protocol are clear. And now we can see why does this actually end up working. So consider a value A that actually belongs to the intersection. So that means that it belongs to both set X and to set Y. Here, if there is such a value, then what happens is that WA is always equal to V of A. And the reason this is that the relationship between V and W is that V of X is equal to delta times U of X plus V of X. And also A belongs to the set Y. That means that Bob would have ensured that A is a root of the polynomial U. And because A is a root, it evaluates to 0. And in effect, you cancel out the effect of delta in this W term, as a result of which W of A is equal to V of A. And in the case that A doesn't belong to the intersection, you have two possibilities. A belongs to, say, Alice's set, but not Bob's set. In this case, Bob can't recognize W of A because delta is unknown to him and delta will randomize the value. So whenever he sees a W of A value, he won't know what the underlying value is because he doesn't know delta. And the other possibility is that maybe A belongs to Bob's set, but not Alice's set. And in this case, W of A would not have been included in the set of values that Alice sends to Bob anyway. So this is why the PSI protocol ends up working. I think there's a good place to take a pause if anyone has any questions.
So I have a quick question. So assuming your OLE construction is perfectly secure, this PSI protocol is also perfectly secure, right?
It's secure in the random oracle model. So this is certainly missing some formal rigor. So
I see. Okay.
Yeah.
Okay.
And it'll also include the assumptions of the vector OLE, which is an LPN assumption. Yeah.
Okay.
Yeah. So now we can switch gears a little bit. Let's think about going beyond private set intersection. So Alice has a set and Bob has a set again. And there have been many applications which led us to ask the question, what if Bob only wants to learn, say, some partial or aggregate information about the intersection? So we want Bob to learn some function of the intersection. So this is a function that both Alice and Bob agree on. And we want to ensure that Bob learns the function of the intersection, but he learns nothing about the actual contents of the intersection. So an example would be, this function could be, say, the cardinality. Okay, and you might wonder, why is it that, where would such a thing be useful, where it's safe to leak the cardinality, but you want to hide the contents of the intersection? So you can think of one example, which is a privacy preserving ride sharing application. So say Alice has her initial location and she wants to go to some destination, and Bob has his location and he wants to go to another destination. It makes sense for Alice and Bob to share a ride if more than 80% of their path is matching. So here you'd want to know the cardinality, and you'd want to know the cardinality to figure out if, say, more than 80% of it is matching, then it makes sense for them to share the cab. If not, it doesn't. And here it becomes immediately clear that both Alice and Bob might not be comfortable to share their exact location, where they're going or the path they're taking with a stranger. Another really popular use case for private computation on set intersection was proposed by Google in their paper in 2017. So they want to compute something known as the intersection sum. And they believe that it's going to be useful to measure the effectiveness of their online advertising. So let me explain this a little more in detail. So Google does a lot of advertising on its platform. And say Google published an ad for Adidas and you were browsing and you saw that advertisement. Later in the day, you went out and you happened to see an Adidas store. And because you saw that ad, you're like, okay, I want to buy that Adidas shoe. You went in and you ended up buying the shoe. So this is a scenario that Google is really interested in. because in some sense, they have influenced you into going and buying that shoe. Or in other words, they have been effective in their online advertising. So the store here has the information of all the people who bought shoes that day, regardless of whether they saw that advertisement or not. So maybe they have the set of all the credit card numbers that made purchases. And they also have the associated value, which I've represented with the set P here. So for each credit card, they will even store how much that credit card was charged for. So what Google wants to learn here is that they want to learn the number of people who saw an advertisement on their platform and then went on to buy a shoe. So that would be the cardinality of the intersection. And they might also want to know the total revenue that was generated as a result of this. So they may want to know the sum of all the payloads represented in this set piece, or in other words, they want to know the total revenue of all the people who viewed an ad and then made an offline purchase. But here it doesn't make sense to reveal the actual contents of the intersection, which would be the people who, or reveal the identities of all the people who bought the shoes. So this is one famous example that has received a lot of attention in recent years and has led people to start thinking about not just the intersection, but computing on the intersection. So now I'll be describing a new result. This is from my paper, Private Set Operations from Oblivious Switching, which appeared at PKC this year. And what we do in this paper is that we propose a new protocol for computing private computation on set intersection, or PCSI for short. And our protocol allows you to compute any function of your choice over the intersection, provided that it's always safe to leak the cardinality. So if you have any application where it's okay to leak the cardinality, then you can apply our protocol. And this allows us to beat the previous state of the art construction, which was given in PSTY 19. So our main result is what we call a permuted characteristic. So we designed a protocol for permuted characteristic, and we use that as a building block to compute any function f over the intersection. And not just that, we also realized that we can use permuted characteristic more directly. So we can use it as a building block to obtain protocols for certain interesting set operations. So the first one is cardinality, which essentially ends up being the permuted characteristic functionality itself. So the minute you have permuted characteristic, you immediately get cardinality. The next one is called intersection sum. And this is what I described in my online advertising example that I just showed you. The third one that we obtain is union. So this doesn't exactly fit into the framework of computing over the intersection, but it's certainly a very useful operation to compute privately. And then we also designed private ID. So private ID was an application proposed by Facebook in this paper that I've mentioned. And we show how we can use our union protocol to realize private ID. And I'll mention that ours is the first construction for private ID, which is dominated only by symmetric key operations. And what you can interpret from this is that if your protocol is dominated by symmetric key operations, it's going to be much faster than earlier protocols which use public key-based operations. So for the rest of this talk, I'll explain what permuted characteristic is and what it gives us. I won't explain how we can get it, and then we'll use permuted characteristic as a building block to see how we can get cardinality, intersection sum, union, and I'll just explain what private ID is. So what is permuted characteristic? So again, Alice has her set X and Bob has his set Y, and Alice chooses a permutation, and this permutation determines the order in which she will place her items. So this is a permutation that she applies to her input set, and Bob ends up learning a bit vector of size n. And let's look at what the property of this bit vector is. So Alice here has permuted her items according to this permutation pi, and Bob learns a bit vector like this. So each bit is associated with each of Alice's items. And whenever the bit vector, say EI, belongs to 1, you can know that Alice's item in that position according to the permutation, that is x of pi I, belongs to Bob's set. That means that x of pi I belongs to the intersection. And whenever EI is 0, it means that that item does not belongs to Bob's set. That means it lies outside the intersection. So here, when you see that E1 is 0, Bob immediately knows that Alice's item in that position lies outside the intersection. When he sees E2 is 1, he knows it lies in the intersection. So it's immediately clear that this gives us cardinality, because the minute Bob looks at his bit vector, he can just count the number of ones in his bit vector. And the number of ones indicate the number of matched items, which gives us the cardinality. And again, you can see that this doesn't reveal the contents of the intersection or the specific values which lie in the intersection. The reason for this is Bob doesn't know the permutation pi, and he doesn't know Alice's set. So he doesn't know what those items actually correspond to. So he can't identify the items in the intersection. He just knows the cardinality. So that's the first set operation that we were looking for. Next, let's look at intersection sum using permuted characteristic. So let's make this more formal. I mean, the functionality of intersection sum. So Alice has her set x, x1 to xn, according to some order. And she also has another set p, which is the payloads, p1 to pn. And this p1 is associated with the value xi, x1, p2 is associated with x2, and so on. Okay. And on Bob's side, he has his set y. And what we want Bob to end up learning is Bob needs to learn the sum of all the payloads for all the items that belong to the intersection. So if only x1 and x2 from Alice's side belongs to the intersection, then we want Bob to learn p1 plus p2. Note that Bob doesn't actually learn the individual values p1 and p2. That's something that we're looking to hide. So this is a kind of aggregate value that we want Bob to learn. Okay, and this is called learning the sum of the payloads of all the values in the intersection. So let's build this functionality. So one thing that we'll be using is PC, but another building block we need is called Oblivious Transfer. So Oblivious Transfer is a technique and a primitive that we see often in secure computation. And it looks like this. So Alice here has the ability to pick two messages, M0 and M1. And Bob has a choice bit. So he can either pick 0 or 1. And based on his choice bit, he ends up learning MB. So he learns message M0 if his choice bit is 0, M1 if his choice bit is 1. If his choice bit was 0, then he has no clue about message M1. So that is a security requirement from Bob's end, that he only learns the message according to his choice bit. From Alice's side, Alice should be completely oblivious of Bob's choice bit. So in a sense, she doesn't know which message was relayed to Bob. She just gets to pick two messages and she has no idea which value Bob ended up learning. So using PC and Oblivious Transfer, we'll be able to design intersection sum. So this is our starting point. We have PC. Alice has her items ordered according to the permutation. Bob has his bit vector. And also Alice has another set which has her payloads. And since she knows the permutation pi and she has chosen it, she can order her payloads or permute her payloads accordingly. So the first step of this protocol is Alice picks n values, one associated with every position, because there are n values. And the property we need is she can pick any values of her choice such that the sum of the Ri values is 0. Once she has this, Alice and Bob are going to run n instances of OT or Oblivious Transfer. And Alice prepares her messages like this. So let's just focus on one position. So say position 3. So here Alice will choose her message 0 as the R3 value that she picked. And she'll make her message 1 R3 plus the payload of the value at that position. So the payload associated with x of pi 3 will be p of pi 3. So the message 1 will be R3 plus p of pi 3. And we know that Bob also has a choice bit for every position. And based on his choice bit, So for E3, his choice bit is 0. He ends up learning a message M3. Because his choice bit was 0, he ends up learning R3. And here, if his choice bit was 1, as shown in the next case, he ends up learning message 1, which would be Rn plus P of pi n. And we can claim that Bob can learn the cardinality sum if he just adds up all the n messages that he receives as output from the OT. So for each OT, he ends up learning one value, M1, M1, M2, M3, so on. And if he just adds them up locally, the claim is that this will give him the sum of the associated values for every item in his intersection. So it might already be clear to some of you, but let's see why this ends up working out. So from Bob's perspective, he's just adding up n messages. So this includes the sum of all the messages whose choice bit is 1 and the sum of all the messages whose choice bit is 0. Now, whenever the choice bit was 1, Bob learns messages of the form Ri plus P of pi I. And whenever his messages have choice bit 0, he learns messages of the form Ri. But nonetheless, notice that each of the Ri values, R1, R2, R3, up to Rn, each of these values appear in the summation. And we know that the sum of these values is 0, so their effect cancels out. And Bob only ends up learning, so only the sum of the payload terms remain. And Bob only ends up learning the sum of the payloads in all those bit positions where his choice bit was 1. So hopefully this is clear. If anyone has any questions, we can discuss. Okay, let's move on to the next set operation. So here we'll be discussing how we can obtain the set union using permuted characteristic, and it follows a similar format. So here Alice has her set and Bob has his set, and we want Bob to learn the union of their sets. So he just ends up learning the set of all the values that belong to both their sets. Another way to interpret union would be that from Bob's perspective, he already knows all the values within his set. So he only needs to learn those values which are unique to Alice and don't belong to his set. And he must learn them in an oblivious manner. And once you do that, you can compute the union. So again, we start with permuted characteristic. And it's the same situation where Alice orders her items according to some permutation. And Bob has his bit vectors. Output from the permuted characteristic. So what is let's interpret what this bit vector means. Again, whenever Bob sees bit vector 0, he knows that Alice's item in that position doesn't belong to his set. And this is some value that he needs to learn in order to compute the union. But whenever Bob's bit vector is 1, that means he already has that item. So he shouldn't learn anything from Alice's side here. So again, we're going to use oblivious transfer. And this is just a quick reminder of what that is. Alice picks 2 messages, Bob has a choice bit, and he only learns that message. From Alice's side, again, it remains, Alice is completely oblivious to which message was relayed. So again, Alice can prepare her OT messages in this manner. She can always pick her message 0 to be the item that she placed in that position. And she can always pick her message 1 to be bought. So here, whenever Bob's choice bit is 0, he ends up learning a value. He ends up learning the value that he needs to. And whenever Bob's choice bit is 1, then he ends up learning nothing or bought, which is exactly what we need. And that's how we get union. Now, let me introduce another functionality. This is called private ID. I won't go into its construction, but I'll at least explain what this gives us. And like I mentioned earlier, we need the union protocol, and we show that union can be used in a nice way to obtain private ID. So private ID was proposed as an application in Facebook's paper in 2020. And what this functionality behaves as follows. So if Alice has her set and Bob has his set, the functionality looks at the set of all possible looks at values from both Alice and Bob and assigns a truly random identifier for each of these values. So here I've taken a small example. If Alice's set is A, B, and C, and Bob's set is C and D, then the functionality will assign a random identifier for each of these values. I've indicated these values as ID underscore A, ID underscore B, ID underscore C, and ID underscore D. And both Alice and Bob learn the set of all these IDs. Additionally, from Alice's perspective, she also learns which of those IDs correspond to her items. So she learns this additional information that ID A corresponds to her item A, ID B corresponds to her item B, and ID C corresponds to her item C. And again, from Bob's side, he can also recognize all the IDs which correspond to his private set. The interesting property about this functionality is that whenever Alice and Bob have a common ID, so in this case, a common value, so in this case, they have a common value C, they end up learning the same common ID. And this is really useful because once say Alice learns the set of all the identifiers, both Alice and Bob can sort their data according to this identifier. And what we can be guaranteed is whenever there's a common item like C, they'll be aligned or placed in the same position by both Alice and Bob, even though they're just working on these identifiers locally. And once you have something like this, once you're guaranteed that every identical item is aligned in a certain sense, Alice and Bob can just go over each of these identifiers and do some further private computation. So you can think of these in the context of something like SQL joins and stuff like that, where common items are aligned and then you can do some post-processing kind of functions. Okay, so we also designed a protocol for this, but I'm not sure if I won't be going into the details. I wasn't sure if I'd had the time. So for the next part, I wanted to bring some context into all these constructions that we're talking about. So we do a lot of experiments, and I wanted to show some real actual numbers on the ground to see where the state of the art is. So we have a LAN setting, and then we have a WAN setting that I've mentioned the parameters of here. And our paper, which computed all these set operations like union and intersection sum, achieved around 2.5 to 3 times lower communication than the previous best paper, which was PSTY 19. And because it has lower communication, we end up with faster running times on slower networks. And let's take a concrete number. So if Alice and Bob are computing on sets which consist of 1 million items, then for cardinality, we were able to reduce the communication from 2.6 GB down to 1 GB. And the previous best runtime was given in PSTY 19, which was around 9 minutes. And we bring it down to 5 minutes in the WAN setting. To compute something like the union, the previous best runtime was given in this paper KRTW19. And their runtime was around 14 minutes in the WAN setting, and we bring it down to 5 minutes. And the third application I mentioned was private ID. And like I said before, ours is the first construction which uses just symmetric key operations. So we do have a little bit more communication because we're not using public key-based operations, but that's also the reason why we have lesser runtime. So we concretely improved the runtime from 6.5 minutes, which was the runtime given in Facebook's paper, down to 2 minutes. And this time the improvement is in the LAN setting. And yeah. And finally, I'd like to share like the different kinds of approaches and the scope of research in this area of study. So the first thing is that, yeah, we've looked at some PSI protocols, and one dimension of research would be asymptotically improving the communication and being more computationally efficient. So, and even concretely, like I just showed you all these numbers. So it's kind of a race to really have really low runtimes for really large sets, so that this can actually become practically realizable and deployed in like actual systems. Another dimension of research is like considering different adversarial models. So in this paper, in this talk, I just talked about passive adversaries where both Alice and Bob stick to the description of the protocol. They don't deviate, but there's certainly stronger adversaries like active adversaries, and it's quite challenging to design PSI protocols for such adversaries. Another direction of research is finding connections between PSI and other primitives. So for instance, I showed you how to design vector OLE, PSI using vector OLE. And in recent years, vector OLE has become really efficient in practice. And there have been some really nice constructions. So it's nice to find a relationship between such primitives and PSI. So that's another area or another dimension through which you can study this problem. And that's another way people are studying it. Another aspect is we just looked at PSI for just two parties. We just considered Alice and Bob, but there could be like three parties or multiple parties. So that's another way. And here it's interesting to define what privacy would mean when there are multiple parties and designing protocols in such a setting. Another way to look at this problem is threshold PSI. So you could set a threshold. You can say that, okay, if the intersection is more than 50% of the number of items, then reveal the contents of the intersection to Bob. If it's less than 50%, or if the intersection is not high enough, then don't reveal anything to Bob. Okay, so this would be useful in certain applications. And another way to work in this area would be like just basically designing better data structures for PSI. So this is kind of the main contribution of my recent paper at Crypto, where we designed a new data structure called Oblivious Key Value Stores. And immediately that improved almost all existing PSI constructions, just because we built a better data structure to handle certain aspects of PSI protocols. And then the second half of my talk was about computing beyond just the set operation and looking at other set operations. So people are also looking at computing things like SQL operations, like joins privately. Another observation is that you want the secret shared output of the intersection. So maybe Alice and Bob want to learn the output of the intersection, but in a secret shared way. And people have realized that once you have this, then it's very easy to do private computation on the set intersection. So even designing how we can get secret shared output is really interesting. You could do something like fuzzy PSI, where you want to see if two items match approximately. Like maybe you're comparing two passwords and there's a typo in one of the passwords. So almost say 9 out of 10 characters match. So that would be an approximate match. So how would you design PSI where you're allowing room for approximation? So clearly in this talk, I've just scratched the surface of the possibilities. And there are many ways in which you can study this problem. It's really interesting and there's a lot happening. Below, I have mentioned like some of the recent works in PSI in the semi-honest and malicious setting. This is by no means exhaustive. Yeah, so I'll stop here. Thank you so much for your attention. I'm happy to take any questions and hopefully this was useful and you learned something.
Okay, thanks a lot, Gayatri. That was really a very wonderful talk, especially the last slide where you kind of gave a very nice overview of the entire domain. What are the various settings, challenges that we are having in this area? So yes, questions from the audience, please. You can unmute yourself and ask questions.
Hello, Gayatri. I think it was really an excellent talk. Yeah,
Thank
thanks for
you so
that.
much. Yeah.
So my question is, so this private set intersection is basically fundamentally dependent on the notion of membership, right? Something belongs to or not, right?
Right.
But then many times this membership may not be, very defined in a clear manner. Okay, so let me give you an example. So we can try to apply these things to, for instance, biometric matching, right? So
Yeah.
Aadhaar-like setting. Okay, so there's nothing, and because the biometric, what we capture, those impressions are not, they're noisy, right? I mean, you don't get the same thing, right? So here it will always be, I think, a nice extension if we can also take in a sort of distance, Okay, so
Right.
I mean, membership, yes, but membership up to something notion, right? Up to some
Yeah.
distance. So I
Yeah.
think that would be a really very useful line of work, I guess.
Yeah, that's an excellent point, and that's something that we're actively looking at. I mentioned threshold PSI, so that would be one solution, right? So that's a really nice example of biometric matching, because in biometrics, you might not have an exact match. So when you're comparing to biometrics, you could say that if there's more than 80% matching, like if it beats a certain threshold, it could match, or, like the fuzzy PSI. So it's like the two values are really similar, so you could have like a distance function and you could geometrically place these values and do that. So yeah, there
Right.
is
So you
some
think that
interesting
your
direction.
protocols will not scale like in a straightforward way, or a lot of work you think is needed in that direction?
A lot of work is needed in the direction. So if you look at a lot of PSI protocols, it's like most of the times it's about you're going to use a lot of combinatorial tricks, and you're going to use hashing and things like that. So the minute you have hashing, it rules out the possibility of having approximate matching, right? Because of the avalanche effect.
Oh, yeah.
So most of the techniques that I'm aware of certainly use hashing at some point. And yeah, you
And
need a
also scale
completely
is a
different
factor.
approach to handle this. Yeah.
And scale is
Sorry?
a factor. And if we speak about other, privacy preserving identification, then we are talking about 1.3 billion
Yeah,
entries. Right? So it's
right.
a
Exactly.
huge scale. Yeah.
Exactly. So it's like a big race. I mean, you always consider sets of 1 million, and then you want to see like how fast it is. So I didn't like have it in my slides, but currently the state of the art is for semi-honest PSI. If you want to compute the intersection for 1 million items, it's in the order of seconds now. So around like a
Oh,
couple of seconds. So that's good. But if you actually look at real world data in the industry and stuff, they're aiming for numbers like 10 million, 1 billion, because that's only when
oh.
like those are the data sets that people are looking at. Yeah.
So
And it's
sorry.
not
So
easy. So these protocols won't extend or perform very well with very large sets. You'll need different techniques.
So
Yeah.
and some
But
more thing. Yeah. So
yeah.
recently, I've also been interested in privacy preserving ride-hailing services. You think that PSI can have any application there? So for example,
The
setting,
ride sharing
how do you want to
service.
make it
Yeah.
a ride sharing? Yes, or ride hailing, whatever.
Right, for sure it will. For sure it will. I mean, it would be like it would be a little bit like how would you translate I mean, it would be like I would think it would fall within the domain of like fuzzy PSI,
Right.
because
Again.
it's more geometric information, right? So if
Yeah.
Alice is in a certain position, maybe you can draw a radius around her, and then it would be like matching between two radii or something like that.
But
Does that make
make
sense?
things more complicated, we can also bring in traffic information, right? that's
For
no longer
sure, yeah.
geometric. Yes. Okay. Sure. Yeah. Great.
Yeah, yeah,
Thanks.
but placing that information geometrically, and yeah, that would be a little bit more challenging.
Great. Okay. Perfect. Thanks a lot. Thank you.
Thank you.
Gayatri, can I ask a question
Yes.
on the hashing
Yeah, for
part?
sure.
Yeah.
Yeah.
So you mentioned about the hashing thing. So there are the techniques known as this location preserving hashing and then location sensitive hashing. Do you think any of
Okay.
those would be useful from the perspective of the biometric thing that Professor Srinivas Vivek mentioned by any chance?
Yeah. I can very recently I became aware of this kind of hashing. I don't know the exact details, but in a certain context, we were thinking that this would be useful. Yeah, for sure. I think it'd be useful in something like fuzzy PSI. Yeah. But I'm not like very aware of the exact definition of this location sensitive hashing. But I think it's like if you compute a hash value, you learn say a set of values, and you compute another hash value, you learn a set of values, and I think you'd have some common values within their sets if they're nearby or something. Is that right?
Correct. Yeah.
Right. Yeah.
Correct.
Yeah, I can imagine. I can see how they'd be useful. I don't know if I'm not sure if it's already been used to do PSI, but I've not come across anything.
Yeah, there have been some work in that
Yeah.
direction. So I was also looking.
Right.
Thank you. Thank you.
Yeah, that's a really good point. Yeah.
Hello, this is Roland. Thank you very
Hello.
much. That was an excellent talk, very clear and very well presented.
Oh, thank you so much.
I work in the field of automotive electronics and software, and there's
Okay.
also overlap with cybersecurity issues because the connected car exposes a lot of attack surfaces. So I was very interested to learn about, you mentioned, and what also Professor Vivek then discussed, applications in the broad space, for example, of ride sharing and ride hailing.
Right.
Did you come across any literature where, other topics regarding connected car data where this private set intersection could be used, or those protocols could be used?
Uh, other, sorry, I couldn't follow that.
The
So the
other
other related.
application fields, like, in ride hailing, ride sharing, sharing locations is, of
Hmm.
course, one topic there. But if you look at connected car data, and there will be a lot of car data being shared,
Hmm.
principle, the car can generate also terabytes of data, which is not shared now to the cloud or with cars, communicating with each other, but there will be more data being shared. And now a lot of companies have started to open up their portals so you can
Hmm.
access your own data, which goes into the cloud.
Yeah.
You can also share data.
Yeah.
So when you looked at your literature there, did you come across any of that type applications where those protocols were looked
Oh.
into for connected car data sharing in an active
Oh,
manner?
okay. So I haven't seen that application appear anywhere, but it sounds very convincing to me that you could use something like PSI there, because if each car is collecting a lot of data, and it would be nice to compute on them in a privacy preserving way if they're opening it up. So maybe something like, I don't know, at an intersection, like I can imagine at a traffic intersection, you'd want to know all the cars that are in that intersection, and I don't know, figure out some ordering of who goes first, or I don't know,
Exactly.
something
Yes.
along those lines. Yeah, but I have never come across this connected car information application. Yeah, I've never seen that in the
Mhm.
literature.
I have a second question related to that, the type of data that is being looked at and shared.
Right.
Is there also some data like measurement data or time series data that is being classified and then looked at and shared for some applications there? Because you already very nicely explained that it's looked into for, advertisement and, and then in this commercial space. But if you look at time series data, um,
Mm. So I'm not aware of that. So when you say series, you mean more like continuous kind of
yes,
data? Is that
yes,
what you mean?
continuous data, sample data,
Mm.
similar data coming
Yeah.
from different sources and
Yeah.
similarity patterns there that
Yeah.
shared. No?
Yeah, I think it's still a very new and emerging kind of field. So all these PSI protocols, like, it started gaining popularity like 4 or 5 years ago from 2016. So people are still working on like discrete data, and that itself is getting is quite hard. So I can imagine that like
Sure.
working with real-time data, it's going to take a while, and it would require a completely different mindset, because yeah, most of the techniques that we use, or the ones that I can think of, uh, assume that the data is like discrete and integer, that kind of data.
Mhm. Yes. Yeah.
Yeah, but
Thank you very
definitely
much.
interesting. I can imagine, yeah, maybe 5 years down the line, hopefully
Yeah,
we'll have
exactly.
things.
Because the type of data, and intersecting data,
Yeah,
that is endless in terms of, the possibilities there to come if you
exactly.
hear it.
Yeah.
Maybe
Mm.
one last question I have, is there any kind of application of quantum computers, either in the adversary role or in the kind of protocol design role?
Yeah, so I will say that I'm not an expert on this, but I will tell you what I do know. So most of whenever we design protocols, we make certain assumptions. So you like I mean, maybe to use vector OLE, you'd need an LPN assumption, which is some cryptographic assumption that you make, or you would make a random oracle assumption, and that would allow you to use a hash function. So these are some assumptions that you make whenever you design a protocol, and a protocol is secure assuming that this assumption holds. So I think post-quantum secure protocols would mean that we need to design protocols with assumptions that are post-quantum secure. So I think it would be in that way that we'd address like quantum computing.
Mhm.
At least that's what I understand. So like figuring out which assumptions are going to be robust against quantum computers, or designing these underlying primitives which are secure against,
Mhm.
which are post-quantum secure. Yeah. So
Yes. Okay.
that's
Excellent.
the role that it would have, or that's how
Mhm.
it would intersect with this area.
Gayathri, thank you very much.
Thank you so much.
So I think Annapurna had a question in the chat. So she asked that
Okay.
if you take the union problem, set union problem, so the party who learns the union, won't that party learn the input of the other party from his own set and the union?
Yeah, that's a nice question. So for example, basically from Bob's perspective, he doesn't know which. So if you look at Bob's set, it was, let me go back to that slide. Yeah.
Yeah, sure.
I think that'll be a better way to explain it. But basically, Bob doesn't learn which of his items also belong to Alice. So the intersection part of their set is what remains hidden.
Okay,
So
okay,
it's
got
not
it.
at all trivial to actually compute the union. It's much harder. Sorry about this. Or animations. Right. So here the union will give you the set of all values. And just look at Bob's set here. So Bob's set are the letters T, A, L, and K. But just by looking at the union, Bob won't figure out which of these values belong to Alice's set. So he doesn't know where that T, A, and L also belong to Alice's set. Or
that's the security you want to achieve in this context.
That is the security you want to achieve. So Bob is completely oblivious of what the intersecting aspect of his set is with Alice's set. So that's what needs to be hidden. And it's very interesting because it seems like they're so closely connected, but actually you need a completely different mindset to obtain private set union. And you saw like there have been many protocols in the last 5 years, and none of them like actually immediately give us a direct way to do union. We had to do like computing on the intersection and a completely different approach to get union. So this is just the second construction for union, if I'm not wrong.
Okay. And I can read some.
Sorry?
One more question, Gayathri.
Sure.
You mentioned with PC, the LIs is going to permute his input, permute her input, so that Bob will only know the cardinality of the intersection and he'll not know the exact elements of the intersection.
Right.
What
so
if
which one are you talking about? Sorry?
Yeah, intersection, cardinality of the intersection. Maybe the previous slide.
Yeah. Okay, I can go there. Yeah.
In this setting, what if we operate with a single element? What if we ask number of queries with single element?
Yeah. So
is it possible him to ask number of queries? Like how exactly is the adversarial model in this setting?
Right. So I understand what you're trying to say. So if there's just one element from one party and the other party has a large set, is that what you're trying to say? Yeah, so that is called unbalanced PSI, and that's really, really challenging. So that's a whole area by itself. And you need to completely different mindset in order to hide like a small number of queries from one party and a large number of queries from the other party. So it would require different techniques. So for this, in this context, what I'm going to say is that the protocols that I mentioned assume that both Alice and Bob have the same number of items. Or at the very least, we're going to assume that they're very close to each other so that Alice or Bob can add a few dummy items and they're equal. And this will require, and we design certain kinds of protocols when the set sizes are comparable. But it's a whole other field when the set sizes are not comparable. I can give you a nice example. Like, for example, if you have a mobile computing device and you want to do a set intersection with a really large server somewhere, there's a huge imbalance in the kind of computational resources you'll have, and also maybe the data sets that you'll have. So yeah, it's quite challenging actually to do unbalanced PSI. And we don't have that very many efficient protocols for it also.
Okay. Yeah. Thanks, Gayatri.
Yeah, sure.
So I can read a couple of chat messages. Professor PK Shrikant said, excellent talk, Gayatri, and great work. Congratulations. And
Great. Thank
Professor
you so much,
Jaya
sir.
saying, great talk, Gayatri. Congratulations on your papers. So indeed, it was really a very great talk. I
Okay,
really
thank you so
enjoyed
much.
it.
Yeah.
And are there any other questions? Not. Thanks a lot, Gayatri, for joining.
Yeah.
And see you later sometime. Bye.
Yeah, for sure. I mean, thank you so much. It was really nice
Okay.
to do this. And thank you,
Thank you.
Professor Shrikant and Professor Jaya. It means a lot.